There you are, folks. Smile. You're on candy camera. Should have shaved today, huh? All right. Yesterday we started talking about confidence intervals. Last 2 days we dealt with confidence intervals. Once again, our goal with confidence intervals is to get a range of values. We're talking about a range of values for our population mean, because getting the population mean may not be, we may not be able to do it, okay? And most of the time, population means are difficult because the population is so huge. If you're talking about a presidential election, we're not doing the survey with the presidential election and interviewing everybody in the United States who they're going to vote for. Okay, we don't have that time. But we can get a good sample, and we can get, with that sample, utilize that sample to be able to guesstimate what the population mean would be. And when we talk about the confidence intervals, we're looking at values where we have X bar, we find our confidence intervals. We have X bar plus or minus our Z for the standard deviation, okay, or Z for the confidence interval, times the standard deviation divided by the square root of n. And as we talked about yesterday, if we don't have a population mean, we can also use our sample mean up there. Okay, if you have a population mean, yeah, you want to use that, but if you have a sample mean, you want to use that. The confidence intervals we basically will be dealing with is 90%, 95%, and 99% confidence intervals. Okay, the values for those I gave you yesterday in the table. I'm going to give you what is called a t-table today. And that t-table, they're even easier to find, and you do not have to memorize those values. You'll get used to utilizing those values, though, and you'll get used to being able to come up with those values. Had a worksheet dealt with confidence intervals. It is basically the same calculations each and every time, except for you're changing your z values. Solutions were provided for you. Any questions you have on any of the problems? Once again, this tends to be one of the easier topics that people will consider, or people will do in the class, being able to calculate our confidence intervals. All right, we're going to move on. You're going to get 2 sheets of paper today, because when we're dealing with the confidence intervals that we talked about yesterday, we were using a z-value. When we use that z-value, what we expect is that the population, or the sample that we're taking, is greater than the value of 30. Problem is what happens if we don't have something greater than the value of 30? We still want to be able to guesstimate. We still want to be able to calculate some values there and get a good guesstimation of a population mean. Once again, statisticians, they just want numbers that would work, that they can get a good guesstimate there. Mathematicians want exactness, okay? Statisticians are okay with, okay, I can get a range of values that will work, and at least I get a good guesstimate there. The second thing I'm handing out here is a t-table. We have a t-table on the front, and we have what is called a chi-squared on the back. We'll use the chi-squared later or sometime next week, we'll use our chi-squared table. This t-table is something that you will utilize throughout the rest of the class. We'll go through this in a minute. But the question is, what happens when our population is less than 30? We still want, or our sample size is less than 30. We still want to be able to get a good guesstimate there with our population mean. Okay? So what we utilize to be able to do this is what is called a t-distribution. A t-distribution is utilized when our sample size is less than the value of 30. Once again, statisticians still want to get a good estimate of the population. Our population mean, our population standard deviation, whatever our population parameter is. We'll talk about a proportion later or beginning of next week, and that gives us our percents. When dealing with a t-distribution, the z-distribution, we dealt with characteristics that you had to maintain or that you had to give me on the last quiz. We still maintain with a t-distribution, it's still going to be a bell-shaped curve. It's still going to be symmetric about the mean. So we still got a bell-shaped curve, just like a normal bell-shaped normal distribution. It's still a bell-shaped curve. It's still symmetric about the mean. The mean, median, mode are still located at the center of the distribution, equal to 0. So we still have these characteristics, and these are all characteristics that we utilize with a normal bell-shaped curve and the z-distribution. We still maintain these things. And the curve never touches the x-axis. It's asymptotic to the x-axis. So everything's going to look the same as what we've done already. But we have some characteristics for the t-distribution that's different than a normal distribution and a z-distribution. Okay, and on our next quiz, you're going to have to give me a characteristic or two that's unique to a t-distribution. The first one, the variance is going to be greater than 1, which means our standard deviation is going to be greater than 1. Okay, if you remember our z-score, we went out by 0, 1s, 2s, 3s, and that was our standard deviations. We no longer have that with a t-distribution. Your variance is greater than 1. Your t-distribution is a family of bell-shaped curves based on a degree of freedom, which is based on your sample size. So what we have is we have a family of curves based on a degree of freedom. Very complicated mathematical computation. Based on the sample size. And the third characteristic, as sample size increases, once again, you get to the law of large number idea. As sample size increases, the t-distribution approaches a standard normal distribution. So as sample sizes increase, it's going to be going back to what we did with our normal distribution, our z-values, what we've dealt with up till now. A normal bell-shaped curve. And that's as n increases or sample size increases. We have our normal distribution. The t-distribution is a family of curves. It's going to look the same. But what happens as n decreases? As your sample size decreases, the hump on Sally the camel starts to rise. So we start getting a family of curves. As the sample size decreases, the hump on Sally the camel starts to rise. And you have a family of curves. You have a bunch of curves. And as sample size increases, we go back to what is close to our normal distribution. But the hump on Sally the camel starts to rise. It still looks like a normal bell-shaped curve, but it just gets a little bit more narrow. It's like taking your hands on both sides on Sally the camel and squish the hump. So when you squish the hump, it starts popping up a little bit more. That's what you have. Now, we've dealt with a lot of mathematical computations here and statistics. Nothing overly hard, but our degree of freedom here is probably going to be the most complicated one. How we calculate the degree of freedom? You ready for this? Hold on. It's your sample size, n minus 1. Whew. That's going to be a toughie. So if your sample size is 20, your degree of freedom will be 19. And you can almost do that without a calculator. I'm hoping I don't start hearing the clickety-clacking. Now, your boundary values. Okay, our boundary values for this population mean. Once again, our population mean. We're trying to get boundary values for a maximum and minimum number and a confidence level for that maximum and minimum number. Okay, these boundary values is going to be calculated very similar to what we just did. The population mean is going to be somewhere between a sample mean there. Sample mean, our t for the confidence interval, times the standard deviation divided by the square root of n. It is the exact same computation, except for I took the z out and I replaced it with a t. So this confidence interval is going to be very similar. How we calculate it is going to be the same, except for it's going to be a different value. We don't have the 1.65, the 1.96, 2.5. We don't have those values. Okay, I don't have like a table that I gave you yesterday. These are for this confidence interval. This is your z value. Okay, but what we have is a t table, which I handed out. So if you pull out the t table, take a look at the t table. What's nice about this t table is if you look along the very top of the table, the first row on the top of the table gives us what is your confidence interval. What are we looking for with our confidence interval? We have a 50%, we have an 80%, 90%, 95%, 98%, 99% confidence interval. So whatever your confidence interval is, it's along the top. That's why I said yesterday, just pull the values off your homework or off the notes, because you're going to be given a table that's going to be allowing us to get these values. So along the top tells us our confidence interval. along the left-hand side. We looked at the column on the left-hand side. You have DF there. That's your degree of freedom. So your degree of freedom that you're calculating here, whatever your degree of freedom is, you're going to slide down to that degree of freedom. Once you slide down to that degree of freedom, you'll slide across the table to your correct confidence interval. If we take a look at the bottom of the table, because it takes us down to a degree of freedom of 28, and then it stops. Because the next row down there is a z-value. The z-values that I gave you yesterday in your notes, your z-values you can find at the very bottom of this chart here. If we look at a 95% confidence interval, the z-value for the 96% confidence interval, or 95%, I take my z-value row at the bottom, slide it over to the 95% confidence interval, I get the 1.96, which is the value that we utilized yesterday. Now the one that's, they take it out to 3 decimal places, which is fine rather than 2. The 90% confidence interval at the very bottom has 1.645. You can utilize that, or they have, if you go to the B down there, sometimes it's used just 1.65. I would accept either one. If you use 1.645 or 1.65. If you use 2.58 for 99%, that is fine. If you use 2.576, that is fine also. And they even have them at the bottom here with the little letters there. Are those called footnotes? I don't know. It's an English thing. Let's take a look at the problem. Obviously, this is a dated problem because if you try to fill up your gas tank right now, unless you're 3/4 full already, you're not just putting $18.53 into your gas tank. If you let it drop to 1/4 of a tank, or less than 1/4 of a tank, then you're filling up the gas tank. Ouch. Your mom or dad better slip you 2 20s rather than just 120. Recent study of 25 students showed that they spent an average of $18.53 for gasoline per week. The standard deviation of the sample is $3. Find the 90% confidence interval for the true mean. So what we have here, we have sample size 25. Their mean $18.53. We have their standard deviation is $3. Once again, this could be population or sample, it does not matter. And our confidence interval is 90%. We have a sample size of 25. What's our degree of freedom, Jalen? Sample size is 25. What's our degree of freedom? How do we calculate degree of freedom? How do we calculate degree of freedom? How do we calculate it? What do we do on the front side of your paper? Degree of freedom, how do we calculate it? Calculate it.
Sample size and minus 1.
So if I have a sample size of 25, what's my degree of freedom?
24.
There you go. Winner, winner, chicken dinner. We have 24 there. Okay, we have a sample size of 25. We are smaller than 30. So we have to look at a degree of freedom. Our degree of freedom is 24. So let's look for the confidence interval, the t-value for that confidence interval. So we go to the degree of freedom. We slide down to our degree of freedom of 24. Then we slide across to the confidence interval of 90%. What is our t value that we will have there? Vanessa?
1.711.
1.711. Anybody having difficulty finding that from the table? So we're talking about our true population mean now. We're going to be somewhere in between. We're going to be 90% confident we're going to be somewhere in between these two values. So we have our t value for the confidence interval. I'm sorry, x bar minus our t value for the confidence interval, standard deviation, divided by the square root of n, and x bar plus the t for the confidence interval, standard deviation divided by the square root of n. And once again, this could be sigma, this could be s. I think the standard deviation for the sample is 3, so this would be an s. So go ahead, calculate. What's our two boundary values for the population mean? Check your answer with somebody around you. Now remember, this is square root of n, so we don't go square root of the degree of freedom. That's a common mistake. We still use n up here when we do our calculations. Okay, degree of freedom just allows us to be able to find the value in our table. This is square root of n here. Jared, what do you get for your two values?
17.55 and 19.61.
Can we change that into dollars and cents? $17.55 and $19.61. Is that okay? We good with those numbers? Good? Yes, no, maybe so? Paul, we good with those? All right. Okay. Once again, we need to complete our problem by, yeah.
Sorry, I got 19.56 and 17.5.
$17.50.
Yeah.
$17.50 and $19.56.
Yeah.
Is that better? All right. So $17.50 and $19.56. You're clickety clack it through. Okay. We better with these numbers? All right. Once again, this is a guesstimate for the population mean. We finish off our work and our problem by writing our statement. We are 90% confident the population mean is between $17.50 and $19.56. So you finish off your confidence interval statement or problem by writing your statement that you're confident that your population mean is between this value and this value. As we talked about yesterday, and we're going to do a problem with it now. When you talk about confidence, okay, yeah, if you want to be more confident that the population mean is interval, you must be willing to trade off a bigger confidence interval. To be able to find a confidence interval for sample size must be large enough. We want to try to use above 30 if we can. If we can't get above 30, that is fine. We still want to make calculations. Okay, and that's what the t substitution is, and the t value will allow us to do. Okay, if you're given a maximum error, if you're given a maximum error that you want with your problem, once again, your maximum error is your mean plus or minus this error that you're talking about here. If you're given the error and you want to find, well, what sample size do I need to get to be able to allow this type of error? Well, this error is your z or your t for the confidence interval, whatever your confidence interval is, times our standard deviation divided by the square root of n. If we solve this for n, because we want to try to get a sample size that is big enough. We don't want to be a small sample size because a smaller sample size is not a good indication of what's occurring a lot of times. It's once again, we talk about the sportscasters and all that stuff. Charles Barkley sits there on TNT and sits there, oh, well, this is just a small sample size. This is a small sample size. We don't know for sure this is what this person will score a rebound per game because we just have a small sample size there. It makes him sound really intelligent. What he's trying to say is we just don't have enough games that is sitting there. So we want to try to get a bigger sample size. So we want to utilize our z value for a confidence interval. That's going to increase our sample size. So if we look at the previous problem, and we say our maximum error we want to be only 50 cents, what would the sample size have to be in the previous problem so that my error would be only 50 cents? Well, in the previous problem, we're looking at a 90% confidence interval. We would like to find our z value for the 90% confidence interval. We have a standard deviation of $3, and we have this error to be only 50 cents. Watch your decimal places. Well, if we take a look at z for that confidence interval, we look at we look at 90% confidence interval, and we drop our t table down to the z value at the very bottom. Once again, we can either use the 1.65 or 1.645. I'm just going to use 1.65. What we can now do is calculate what would be our minimum sample size that we would require to have only a 50-cent error. That means we'll have plus or minus 50 cents. Or our sample size is our z value times the standard deviation divided by the error. but then we have to make sure we square that. Remember to make sure we square it as we go through this. Emma, what did it come down to? 98.01. Okay, now we're talking about a sample size. So if we're talking about a sample size, we're talking about actual cars filling up and students filling up. What do you think we should take that to? 99. Because 98 would not quite get us that air. So what we want to do, you always round up when you're talking about how many. So we want to go to 99. We want to sample 99. And once again, as we talk about this air, what we are looking at here with respect to a confidence interval, we are looking at for our confidence interval, we have our X bar plus or minus this air for the population mean. We have 1853 minus a 0.50 and 1853 plus the 0.50 or 50 cents there. So what we want with this is we want our population mean to be somewhere between $19.03. Oopsie, how about $18.03 and 1903. So we want our confidence level or confidence interval for our population mean to be anywhere from $18.03 to $19.03. That's what we're doing with respect to this air and saying this air is 50 cents. Okay, we want our range of values here to be between basically $18 and $19. Questions you have? Once again, basically the same calculations. Now you're going to need your calculator here. We're going to go through one problem from the homework. It's going to be a little KYC activity here. So we need to know our calculator, what it can do. And if you don't have a TI calculator, you might want to get one. At least borrow one for a class. Let's take a look at problem number 3. We have a sample of 17 states that had these cigarette taxes. In cents. What's your point estimate? Well, when I'm talking about a point estimate, what's our best point estimate? From yesterday, how do we find our point estimate? Best point estimate is the what, Ella? The mean. And to better classify the mean is what type mean? Anybody? Not population. Sample mean. The sample mean. This is a sample of states. Well, I don't give you any data here except for the values. But if we take a look at our calculator, I want you to hit your stat button. And what we're going to do is utilize our calculator to be able to calculate our values that we need. If we go to stat and we want to edit, what this will allow us to do, well, I see I got values in here. Okay, if you have values that are listed in here, okay, how we can correct that, we hit our second button and our plus button. And option number 4 is clear all list. Now if we go to stat and edit, your lists are clear. You don't want to go up to L1 and hit delete, because what it's going to do is delete the whole list. And that's not good. Then I have to do some work to be able to figure out how to get it back there. Okay, everybody there? What we're going to want to type in is we're going to want to type in all of our data values. So just type in into L1 your 112, 120, 98, 55, 71, 35, 99, 124, 64. What we are given in every one of these problems is sample mean and standard deviations. That's what's given to you. All I give you in problem 3 is data values. So what you need to do is generate your sample mean and also a sample standard deviation, because this is a sample. So if we go back to stat again, hit your stat button, hit your right arrow to go over calculate. The first option there is one variable statistics. Go ahead and hit enter. You get one variable statistics and hit enter one more time. What it will give you all your statistical data that you need. What we want is we want the sample mean and the sample standard deviation. Well, line 1 gives us our sample mean, 87.375. So what you should do in your paper, write down, what is my sample mean? What's my X bar? And then what is my sample standard deviation? Okay, my sample standard deviation, I have 36.39. I guess if we go 1, you can go 3.9, or if you want to go 4, that's fine, 0.4. But it will give us our sample standard deviation and sample mean. Hopefully you get to save. Sometimes I don't get all the calculations up there. I typed in all my data values and I don't get them. I'm missing a value of my data value. Am I good with it? The 87.375 and the 36?
I got 91.06.
91.06. One of my data values is probably bad. If I go to edit,
There's 2 150s.
I got 2 150s there. All right. So there's 2 on here.
Yeah.
All right. Sometimes I don't get all my data values up there correctly, which is fine. You pull off your calculator from your calculator what your X bar is and what is your sample standard deviation. Okay, once again, my values might be a little off. Okay. But then you can go ahead and calculate your values at that point. You can find your point estimate is your sample mean, and then calculate your 95% confidence interval. Questions you have? Monday we'll deal with population confidence interval, and Tuesday will be standard deviation confidence intervals. Question?
Oh, yeah, which one is the standard deviation? Is it
Your S.
the S?
Yep. Your sigma would be your population standard deviation. And what we're given here is a set of sample values here. So if this is sample, I'm talking about sample standard deviation, that's my S value. When I talk about my population, once again, that's your sigma value. All right, the rest of the time is yours.